All right, let's start. Number 2, find A, B, and H. Is this the right problem? Okay, sometimes I prep the wrong problem, so I need to know that right away. So that I should have brought that up. Be careful when you do the problems. So I think they move the problem number around. Sometimes it's below the diagram, sometimes it's above the diagram. Yeah, so just be careful. Like, yeah, you can do the wrong one. If you do the wrong one, you're gonna realize it right away. Don't worry about it. I should turn the music off. It's a good song. All right. Don't worry about it. I'll still give you credit for doing the wrong problem as long as you did it right. So there you go. All right. Any questions on this one? How'd you do it?
I have a question.
Yeah.
Do we get extra credit for doing extra problems?
Absolutely not. You actually get extra good karma credit, right? You get extra knowledge. You get extra a lot of things, but yeah, no. I like it though. I really do like it. You will get extra credit assignments. So when those come, just nail it. All right, how'd you do this? How'd you find A? Sine 48. So trying to find A. So we know that angle A is 48 degrees, right? And we know C is 25 feet. Yeah. So we can go sine of 48 degrees equals what? Opposite over hypotenuse. And we can use that because this is what kind of triangle? Right triangle. Exactly. So we're looking at opposite A over 25. Does this look right? Yeah? What did we get for A? 18.58 feet. And that's rounded? Yeah. Perfect. Questions? This is not going to get any easier than this. It's only going to get harder in this life. But that's good. We want to just rack these points up while we can, right? So it should look something like that at the minimum, right? I should see the formula. It's okay that the formula is filled in. You could have written the formula first and then fill in the formula. That's nice too. As it gets more complicated, that's nice. If I see the formula first and then fill it in. If it's simple stuff like this, that's fine. Good. What else do we have to find? B, how'd we get it? So 42 is here. How'd you get that? Yeah, so interior angles of 180, and we have 90 up here. Excellent. And doing the sine of 42 does not use the number I just calculated, right? So that's another good reason to do that. All right, so sine 42 degrees equals opposite of this angle there, B over what? 25, the hypotenuse. Get those units in there, right? So it's 25 feet, sine of 42 degrees, and then we have B equal, what's our number? Should be less than 25, right? 16.73 feet. Absolutely. Yep. Love it. Cosine of what? Not the 42, right? Yeah, the 48, because we would use adjacent B over the hypotenuse. Again, not using the number that we calculated. Perfect. If we use the number that we calculate, if I did use this 18.58, would I use 18.58? No, use that big long number, right? All right, perfect. Should be just kind of review like. What else? H? How do we get H? So sine of 48, but you're going to focus on this little triangle, right? Yeah. So you're going to go opposite over hypotenuse, which is B, right? Yeah. So if I went sine 48 degrees equals opposite H over B. B is 16.7. Anyone got that number? 72826. So what I said is if you don't store, go at least 4 places. And you'll be good and accurate. 6 is good. Yep. So just don't use the 7.3. That will add inaccuracies to the H solution, okay? So if you use the long form, what is H equal to?
12.431.
4315?
Yeah.
Yeah, so here we would round it in the solution. Good?
Yeah.
Questions? Got to get them answered if you have them on this. If you're looking at this going, what the hell are they doing? Then you got to get that question answered. You got to stay after class and work with trigonometry with me, because after we get through these first ones, I'm just going to assume we can do this stuff. And we will do it like on every problem for quite a while. When we get into vectors, we're just going to be doing a lot of triangles. So if we're given a vector like this, 40 newtons, right, at 27 degrees, I'm going to want to know the X effect and the Y effect of that vector, right? The X effect is what? It's this. And the Y effect is this. And what does that make? A right triangle. Over and over and over and over, okay? And then we're going to like take vectors and we're going to say, oh, we got 100 pounds here. That's a pound symbol. 100 pounds here. And I got 100 pounds here. Right? And poor little point A, what does it feel? What's its full effect? Like, what does it feel? Well, it feels 100, 100, and 100, but that doesn't tell me what it feels, right? So that's just like, oh, we need all these X effects, we need all these Y effects, and we add them all together and we can come up with the X effect and the Y effect, right? And then we can turn that into another result. That's what it feels, which is like 6 triangles. So that's all we do for quite a while. All right, so that's why we grind on this, and I want it as comfortable as possible. How about that one? This is a ladder one, right? Yes. Love ladder problems. We do them all term. You'll never go up a ladder the same way again after this class, especially after we do friction. So we do friction in this class, right? So I love ladder friction problems because if you put the ladder at the right angle, right, and then you put your little person going up the ladder falls and everyone dies. So that's always fun to calculate. When do we fall and die is the question.
Oh, thanks.
But yeah, exactly. Enrique, I love that ladder problems. All right, how do we solve this? Yeah, so because this is what kind of triangle? Yeah, did you have to assume that? Yeah, so it wouldn't hurt to make that assumption, which means you could put a category called assumptions and a colon and then write, I assume this to be a right triangle. Okay, that's really good on quizzes and exams because I make all those, right? And I'm just intentionally, I'm not going to tell you it's a right triangle or not a right triangle. And I want you to make an assumption. Is that a right triangle? If it is, you need to write it so I can then evaluate you on your assumption, right? Whether the assumption is good or bad, I can still see that you made that assumption. And if you made the right choices, calculated it correctly, then it's all good. All right. Oops, already did the S. Sine 70 equals H, right? Opposite over hypotenuse. So let's talk through the algebra in case anyone's having a hard time with that. How do we get the H by itself? Multiply by 28 feet. That's how that happens, right? That's the long form algebra. And then what we do to one side, we have to do to the other side. So this is what? Just a number, right? It's just a number, turn it into a number and then multiply it by 28 feet and you're going to leave H over 1, which is H. What do we get? Wait, Should it be larger or smaller than 28? Yeah, so think about that during every problem. Think about before you calculate it, like, hey, this should be smaller than 28. So then when you calculate 54, you're like, that can't be, right? And then draw your diagrams, like I said before, proportionally right. You don't have to get scale out. You don't have to AutoCAD it up, but that would be cool. But you don't have to do that. But draw it correct. That's gonna really help on these problems. Like all those vectors are 100, make them all the same length. That's gonna help you. Okay. If this is 27 degrees, put your 40 at approximately 27 degrees. Okay, less than 45 type of thing. It will help you. Like, you'll know right away if you're getting a bad answer. All right, what's H? Feet? Yep, and committed. All right, very good. And then that was 6. This is 6, correct?
5.
Oh, is it the right one?
You gave us.
So this is the wrong one.
Yes.
Yeah, see, there we go. Where did I get? Oh yeah, look at that, 5. And then what did I do?
So
Yeah.
we get the extra credit, right?
I get extra credit because I already worked this, but I get extra credit all the time. Wait, I'm trying to figure out how to work my book. Oh. Where's the problems? Oh, here they are. And number 5?
Yes.
This one?
Yes.
Oh, that's weak. I like this one better. It says 2 legs of a right triangle are 6 and 10 foot. Determine the length of the hypotenuse and the angle opposite the short side. Length of the hypotenuse is what? How'd you get that? A squared B squared equals C squared. Take the square root of. So 6 times 6 is 36. And 100 or 10 times 10 is 100. So we're 136 in the square root of that. So it's just over 12. Just under, 144. Yeah, you're right. Okay. I just did that one in my head, so I get extra credit for that.
Sorry.
All right.
Nine.
Damn. And then what was the angle opposite of the 6? Wait, let me think. 10, 6. It's like 30 degrees. Dude, I'm on it. All right. Excellent. Make sure your names are on them. Pass them to your left or to the west. Names are on them, pass them to the left. And then if you're on this left side, you can look at them as they're coming in. And you can look at it and see what their work looks like compared to your work. It's not a competition in this class as to who makes the nicest piece of home.
Thomas, you want to stay blue?
But it is a competition for you're all out there and interviewing for jobs. Just so you know. Your stuff needs to what? You want yours back?
No, this is stable. Thank you.
There is a staple up there if you need to staple it. That does help. Appreciate it. That. It's good, man. Beauteous. Nice job. See? This is mine. Got them all? All right. Excellent. All right, let's do this because I was unhappy with our non-right triangle conversation last time. So I want to work on it some more and I want to kind of clarify a couple things. Non-right triangles, no trig functions. Trig functions are sine, cosine, tangent, arcsine, all that stuff, right? We get these 2 equations for non-rights. We don't actually get into non-rights for a while, but like in friction, we do a lot of non-right triangles. So we'll probably review this again when we get closer. So here's kind of a rule that's going to help you with these, like when to use what. If you have a side and an angle opposite. So two things, side and an angle opposite. You will be able to fill in one of these pieces of the equation. The sine law will work. Okay, so like this one, I have the angle and the side opposite. Right, on this triangle. I have my three things. We know we all need three things. But if you have a side and the angle opposite to the side, then you can fill in one of the pieces of the sine law, and you should be able to write the second piece with just one unknown. Okay, so that's a good rule. When you look at your non-right triangles and you say, oh, I got a side and I got the angle opposite, the sine law should work. Okay, if you don't have that, then you need to have two sides and an angle for the cosine law. So for the cosine law, you're going to need side, angle, side, SAS. And that's going to trigger cosine law. You'll have one of the two. You can't give I guess you could do all three sides and have no angles. And that would also be the cosine law. Because if you can't make one of these work, top and bottom, you can't use the sine law. Okay? You see all that? I know some of you are catching this up, so I'll give you a second. It's gonna be so good at the mountain, just so you all know. It's gonna be so good up there. It's gone from bare to like, it's gonna be really good this week. It's crazy.
Last time I went skiing, I almost break my leg, so I can't do that.
Went 3 feet anew at Ski Bowl, and that's gonna consolidate between now and Friday, and then they're gonna get another foot Friday. So Saturday morning is gonna be like stupid good. Yeah. From no snow, like what, a week ago, like nothing. All right, so let's work this one. So we look at it, we say, oh, we have these three things, that's good. It's a non-right triangle that triggers these two things, right? And I have this angle and opposite sides, so that should trigger sine. So these two are always together. So I can say 40 feet over the sine of 70. And that's what I mean by you can fill in one of the pieces of the sine law, right? There's no variable there. And then you can set it equal to, and obviously we want to use this other piece of information, the 30 foot, right? So then I can say 30 feet over the sine of A. That can give you that angle, all right? With non-rights, you don't get to like choose what you solve for. You just can solve for whatever you can solve for, and then you can move forward and find the other pieces. Okay. So that's the other thing to think about is sometimes with right triangles, you can actually go straight at what you want. But with non-rights, you just get what you can get and then move on to getting the rest of it. Okay. All right. So this is some deeper algebra, I guess. How do we solve for the sine of A? Multiply by 30. Is that what you said? So if I multiply by 30, I'm going to end up with a lot of 30s. But I don't want to do that. I want to get this statement by itself first. That's a great idea. Turn this into a number. This simplifies things. So what is that number? I got it. Anybody else got it? I did not get that. That's the number I got. 42.5671 equals, and I'm going to write it out just so we can see it. So I still need A by itself, and I want A on top. I don't want 1 over A.
From mine, because you want to
Multiply across, I hear that, I like that. So I would multiply by sine A. And that does what? Gets rid of it and puts it on top on this side because of what I do to one side, I gotta do to the other. Sine A. Yeah, we're good with that? So now what? This is the magic of algebra, man. This is good. Divide by 42.5671. And that does that, right? So then I have 42.567, 71, and that's underneath. We're getting there, aren't we? You don't have to show me all these steps unless you're mucking it up. And then you should start showing me those steps. All right, now how do we get A by itself? Because now I have that over 1. This is all gone. Divide by sine, which is the arc sine. Take the arc sine of the other side. So A is going to equal sine minus 1 of 30 feet divided by 42.5671. Yeah? Excellent. That was a lot of like algebra stuff there. A little bit ugly. So the other little tricky rule is just switch places, right? So up here, sine A and 40 can just swap places. Is that correct? Yeah, that's true. And then to clear sine 70, just clear it and bring it over. Take the inverse sine of it and you got it. All right, so what do we get for A? Silence. Say again. 4.81. Anybody else agree?
Yeah.
Ooh. It's risky, isn't it, when you say a number? You just want people to agree. Love it. And that's obviously rounded, right? Good? All right. So if you have that angle and the side opposite, sine law is going to work. Now that I have this, the 44.81, right? Now these two work together. These two work together. I should be able to find B, right? Because I could get this angle from interior angles. Then I could do another sine law to get B. Good? All right. Good refresher. Yeah.
Would all the angles still equal to 180?
Yep. Every triangle. Every triangle. Yep.
For the law.
Yes. For these,
Yeah.
yes, they can flip. Absolutely. Algebraically easier. Yeah, except it hurts my head to flip it. But if you're comfortable flipping it, you can. So when we're saying flipping it, we mean right? It can be written that way and used that way. Either way.
Something else also, a lot of people get confused with the letters. You can move around the letters. It's not just the way that you teach us or somebody else teaches. You can rearrange all the letters.
Especially if the triangle is labeled differently. Absolutely. The important thing is the side and the angle opposite still, that has to be true.
Yeah.
So this could be called apples and this could be called X, right? And it would be X and apples, but yeah. The important thing is that opposite each other. All right, let's do the next one. This one, we do not have an angle opposite a side and we don't have an angle opposite of a side. This tosses out the sine law, can't use it. It's not going to work. You're going to end up with too many variables, right? So when a non-right triangle sets up like this, it is side angle side that triggers the cosine law. Really, we only have those two laws and interior angles. That's all we have, right? So cosine law is this thing, c squared, a squared, b squared, 2ab cosine c. And we're just gonna be able to get what we can get, okay? So this is our C. This would be A and B, or B and A, however you want to put it. It doesn't matter. It can be in any order there. So the equation sets up as C squared equals, I'll call this A, 40 feet squared, plus B, 30 feet. Oh, I'll write it the same way. Squared. And if it helps you, you can write it that way, which means the number gets squared and the unit gets squared, right? So sometimes you'll see it written this way, 40 squared feet squared, right? Because really both things get squared. All right. And then it is minus 2 times the first one, 40 feet, 30 feet, the second one. Those are not squared. And then cosine angle opposite of C, 80 degrees. That's how the equation sets up. And again, you get what you get, and we're gonna get C. Whether that's what we want or not, doesn't matter. But once we have it, then we have an angle and an opposite side. We could go back to the sine law to solve this thing out, right? You just need that first push to get other pieces. Questions? Did you have a question? Did you? No, you're good? All right, how do we get this? We just run all this, right? And then take the square root of it. Yep. All right, do it. See if we can get the same number here. I get 45.64. Yeah. And what's the unit? Feet. Yeah, so we have feet squared plus feet squared. And that's legal because we're adding two of the same thing, right? And then we have feet times feet. What's that? That's feet squared. Cosine of the angle has no unit. So we're still feet squared over here. So then we take this feet squared minus this feet squared, right? Still gives me feet squared. And then I take the square root of it back to feet. Does it make sense? If this is 40, this is 30, and this is 45. That's a 5. Yeah, that makes sense. Looks longer than the 40 to me. Like if I swing this down here on its radius, it's like in there somewhere. But yeah, 45 makes sense. Good? Good, 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 good. All right. We are gonna take an early. All right, a quick conversation about SI units. So in the book, it has this little part of the first chapter. Talks about SI units. We'll do both metric and US. So we got to get comfortable with a Newton, a meter, a millimeter, a centimeter, right? All that kind of stuff. So here's their little table in the book. Right, quantity meter, mass, kilogram, time is still seconds, so that one's pretty universal. Angles can be radians. We will use radians at some point, so we kind of need to know how to go back and forth between radians and degrees. And then we use most of these, not all this term. For example, moment of inertia, we won't use until strength of materials, right? So we're not gonna use all this term, but just note that this is here, right? And if it's not familiar with you and you see something like meters per second squared or something, you could go back to this little table and kind of get a little definition of it. The tricky ones are newtons that students struggle with, because a newton is a thing, but it also has another unit to it. So it's a collection of units. Actually, a pound is a collection of units too. It's a collection of slugs and gravity and those kind of things, but we don't really think about that. We kind of are comfortable with pounds. Newtons, we often have to like dissect them down to the kilogram meter per second square. Okay. So just know that a newton is a force like a pound. So if you see newton show up, it's similar, same thing as pounds, right? It's a force unit. Do they do the subs? Oh, they do. Here's the subs or the prefixes. So giga 10 to the 9th, mega 10 to the 6th. You'll see meganewton. We do that often. You'll see kilonewton very often, right? Because that's thousands of pounds. So what's our kilonewton in the US system? So a newton is a pound. Kilo is 1,000. What's 1,000 pounds in the US system? Or 2,000 pounds? Ton, yeah. So we kind of have the same system. It's just not as straightforward as the metric system. Metric system is so clean. It's really clean because, right? 9, 6, 3, minus 3, minus 6. Like it's easy to keep track of the prefixes where we don't have that. Kilo pound, that's kind of weird. So we do tons instead of that. It's like, what? Where did we come up with that? Anyway, that's here. So if you see a number that's got a G in front of it and you don't remember that's to the 9th, you could go back to this page. I'm an open book kind of guy. And in my opinion, that's an advantage to you, but it's also a disadvantage because during an exam, I'll see a student doing this with their book instead of just thinking, right? You'll just start searching your book to find an example problem like that problem or something. Or you're looking for a piece of information. And if you don't have your book tabbed, you'll spend some time looking for something in your book, right? So tab your book, number one, or keep a note sheet. That's what I like, is a note sheet. So anyway, however you want, right? All right, and the other part of this is, probably on a different page, is unit analysis, which I'm just going to talk about. So we've already done it a little bit, but unit analysis is like if we have 34 inches and I want to turn those into feet, right? Unit analysis is how we do that. And you're all like, well, if you want feet, what do you do to the 34? Divide by 12, right? But the unit analysis of that is using the 12 inches per 1 foot and multiplying. So that's the unit analysis. That's where the units cancel out and give you a new unit, right? Units cancel out and give me a new unit. So this tells me I take the 34, which is over 1, and divide by 12. Okay, so if you have a conversion that you're doing that's not familiar with you, or you need to get to a different unit from giga to mega, right? It's like, I would encourage you not to do that in your head. I would encourage you to write that out. So then you know the units are canceling correctly, and you know you're actually doing the right thing, which is either multiplying by 1,000 or dividing by 1,000, right? So easy to make a mistake just by doing it in your head. Write it out, just like I do it with the trig functions all the time, because it's not always multiply the length times the trig function. Sometimes you're dividing something by something else, right? So just write it out. What's this going to equal? $34 divided by 12, right? 2.83333 feet, correct? If I wanted to round it for the solution, then I would round it. If I wanted to go to inches, how do I do that? Yeah, if I want to take and put it in the form of 2 feet, so many inches. How do I do that? So this is what, 0.8? What's the unit on this? 0.8 feet, right? So I'm like, oh, I have 0.8333 feet. How many inches is that? Well, it's 0.8, so I could write it out. Yep. Because I'm gonna use the 2 as 2 feet, right? And if I want to go back to inches, what do I gotta do? 12 inches per foot. Cross it, it's 12 times the 833. All right, what's that number?
There it all would be 10.
Okay. Actually, is that right? I'm getting 10 flat out. Yeah, 10, darn. I wanted to have another fraction there, so then you had to go to like, oh, how many,
Yeah,
what
I
part of
did
an
that.
inch is that, right?
I
But
get the number.
that was bad luck. 10 inches. Right? 2 feet, 10 inches. So just be careful with the problems. Sometimes they'll ask you for a specific unit. They'll say, what's the answer in feet and inches? And so if you give it in 2.833 feet, that's not feet in inches, that's feet, right? That's gonna be, this is tenths of a foot, this is hundredths of a foot. So you just watch your units and do your unit analysis if you're not sure. This works for conversions too, right? So if I have 450 pounds and I want newtons. This brings up, sometimes I get students that will get a metric problem and they'll convert every number to US. Like, no, don't do that. You're given a metric problem, you gotta work it in the metric system. All right, so how do we do this? You could use Google for sure. Absolutely. Google up the conversion, right? So unfortunately, if this is a homework problem for me, I'm going to want you to show your work. So, but still you could Google the conversion. I'm okay with that, but you got to get the conversion. Back of the book. Actually love this book for this reason. I don't know how to get to the back of my book. Here, I can do chapters all the way to the end. It has some decent conversions in it. I don't know if I'll find them. Can somebody look at your book and see? Connections, columns, no. Moments, area by integration, oh, love that. Steel beams, diagram formulas, average properties of some common materials, I love that table. Design values, properties of structure, dimensional properties, channels, dimensions. Why don't I see it? Okay, maybe it's the front cover. Who's got a book? Gina got a book. Anybody find it?
It's like the first, it's like inside the.
Front cover?
Yeah.
Okay, so I was in the wrong spot. Front cover of the book. Let's see if see if they give me the front cover. Oh, cover. Check it out. Oh, there's that. Okay, I don't want the cover. And then it goes to preface. I don't get the front cover. I want my money back. Yeah, that's bogus. Brief contents, what's that? Oh, detailed contents. Oh, that's cool. Preface. Wow, I don't have the front cover. That's crappy. Anyway,
There's a constant 4.448.
exactly. So read the table to me. What's the top of it say? Like the left column, the top table says what? No, very top. Yeah, conversion factor. She's like, what am I doing wrong? Yeah, so it's pretty good, right? Actually, I want you to say multiply. That's all right. Right, so here's the length, inches multiplied by this to get millimeters. That's how it works. Cool? So essentially, it's just saying, hey, there's 25.4 millimeters for every 1 inch. I really wish they would have put ones in there. I just wrote your book. Sorry. Probably won't be able to return it. You're gonna keep it though, for the rest of your life. Right, so that's how this works. So let's go down and find force. Pounds, 4.448 newtons, right? So we multiply by, so 1 pound equals 4.448 newtons. That makes sense? All right. That's your conversion. 1 pound equals, so 1 over the other, 4.448 newtons. All right, and that's what you're going to use to get to newtons. I probably wouldn't write it that way because I want the newtons on top. So you can write it either way. You can flip it, kind of like the sine law. So if I have 450 pounds, I put that over 1, and I multiply by 4.448 newtons over 1 pound. Unit analysis. That's how we do conversions. Okay. What happens to the pounds? Yeah, go away. And we're left with newtons. There you go. So that actually front cover is pretty good. Dynamics book doesn't have anything like that. Nothing.
By the way, in your PDF, it's page 5.
It is on page 5.
It is,
Why would they put it on page 5?
because it's the front of the book.
Page. Oh, I don't have pages in that cover. So in the introduction,
Be on applied statics and spin material, right at the beginning. Now you're way
so in the preface,
up. You said cover right there, check cover.
so I got cover. I got no pages. I
Go
can't.
down,
It's down to brief contents now. Yeah. Okay. Can I film this? No, that's all I get in the cover. Won't go
I
anywhere.
got the.
You
same-
found it somewhere though.
Yeah, it is on page 5 on the PDF. I got the PDF.
All right, well, I'll look for it. Not wasting more time on it though, because I got the real book coming. All right, questions on that? What's my number? 2001.6. Any more numbers? That's it? And then newtons? Yeah. So I'd probably put the 0 on because we're gonna assume everything to 2 places, right? Oh. What?
I looked it up and so the dude.
Oh, so it went out further?
Yeah, it had 2 twos up.
Oh, okay. So I'm okay with using a conversion out of the book, but that's
I don't know
good.
why I work with metric box systems, and when you do newtons, which I don't like it, the conversion and different website, they give you extra numbers,
Hmm,
but.
it's just more accurate than the book
Yeah,
put down.
but the metric system itself, normally it's 3 digits after the decimal point.
Mhm. It's close enough, especially when we get into the design part of strength of materials. We talk a lot about factor safety. We talk a lot about accuracy, and we talk a lot about like these numbers are super important to keep them very accurate, but we're gonna have these factors of safety on top that are gonna just eliminate any kind of precision like that. How many kilonewtons is this?
2.
Yeah, so 1,000 right? 1,000 newtons per 1 kilonewton. So this is 2.00160 kilonewtons or 2.00 kilonewtons. Right? So when we change the unit, sometimes we lose some accuracy. That's just part of life. All right, good. So now you have some resources for different kinds of unit problems. Any questions on that? We good? Back to the book. Principles of Statics, number 1, chapter 1. I'm starting to figure this out. I want to go to the end of the chapter, so I use these little arrows down here. Whew, struggling. Oh, dang it. That's the part I wanted. Okay. The other thing I like about the book is at the end of the chapters, you have summary by section. Okay. So as we go through our 8 or 9 chapters this term, I'll spend time with the summary by section for every chapter that we're completing. Right? This is a great way to study for an exam or a test. If you understand everything in the summary by chapter, you are ready for whatever is coming on next, right? So, statics deals with the forces and force systems acting on rigid bodies at rest. I don't even know that I told you what statics was. So it's not a bad thing to review. Statics is this study of forces, right? So we're going to have all these forces. And they're going to be on objects at rest. So here's the box at rest. That's the analysis that we're going to do. Now, we will calculate impending motion. An impending motion is just before it moves. In other words, it's going to calculate that maximum force before it moves, and that'll be the information that we want. Because if you put more than that on, it moves, right? So statics does deal with some motion, like when we do friction, we're going to think about things moving, but we do a static analysis where it's not going to move. But we can determine when it would move, right? We just can't determine what that motion would look like with statics. Once it starts to move, that's a dynamic analysis, and that's a different class. Okay? So statics is about collecting all the forces on this building and understanding how they all interact. That's what statics is. When the ground shakes and the building's doing this, that's dynamics. That's a different class. Good? All right, so that's statics, and that's where we're heading. It uses trigonometry. We did that. So 1.3 done. We use numerical accuracy. We talked about that. Check, done. We did dimensional analysis. We just did that. That's the foot, canceling your units out. Check, did that. And then what's this last one? Metric system. Check, did that. Chapter 1's done. Good? All right. So let's go to chapter 2. See what's going on there. So we have 4 qualities of a force. We're going to discuss forces in detail. And we're going to discuss how they act on an object. So chapter 2 is pretty much all about forces. Okay? So let's do that. Let's start. And then we'll probably be done early, which I'm okay with. All right, 4 characteristics of a force. When you give your solutions or share information with somebody else in the engineering world, you need all 4 characteristics. We represent forces as vectors. Vector is a straight line, right? And an arrow at the end. It has 4 characteristics. Let's see if you can guess them without looking in the book to cheat. Ready for guesses. This is a little bit of cheating here. Weight, magnitude, yep. So every force has a magnitude, and that is represented by what? The length of the vector is the magnitude. Okay? So if we say it's 100 pounds, that is the magnitude. There are three more characteristics. Direction. So what's the direction? This is good. I love it. So what represents the direction on a vector? The degree. That's right. This degree of 28 degrees is the direction. So it's the angle. Very good. There's two more. Distance, no, that's a good idea though. I like that idea. Oh, I got a guess. It's a guessing game. So tell me about the 100 pounds. Like, how do we know where it's going? Okay, like, kind of getting there. How do we know that, is it 100 pounds heading to the west? Is it 100 pounds heading to the east? Is it 100 pounds up or down? How do we know?
It's based on X and Y.
It is.
Quadrants.
We're getting closer. Look at the vector though. What tells us which way it's going?
And quadrant number 1 would be X positive and Y positive.
The arrow. That's true too, but we're not going into components here. Those are the effects. The arrow tells me where the 100 pounds is going, right? The angle only tells me the line of action. It could be going this way and the angle is still correct. So the direction doesn't tell you which way it's going on this line of action, right? The arrowhead tells me which way it's going. That makes sense? The arrowhead could be pointing down, could be pointing up. It's pointing up, right? It's called the sense. Yep. The 28 degrees only tells me the angle or the line that it's working. It doesn't tell me whether it's going up and to the right or down and to the left. I could draw this vector just like this. Right? Not the same vector, but the same direction. Absolutely the same direction. Not the same sense. The sense is opposite down here. Right? So the arrow is the sense, which way it's going. So that's the third characteristic. There's one more. It's kind of hard. It's not hard. Let's say, here, I'll give you a hint. Here's a beam. It's okay. Keep you in the dark. Bunch of mushrooms. Directions are the same. Magnitudes are the same. Senses are the same. What's different? Point of application. Exactly. This would be A, and this better not be A. This better be B or something different, right? So there's the four. Magnitude, direction, sense, point of application. I need all four if you're going to give me an answer that is a vector. Okay? Easy way to write it is force equals, this could be, you know, force of A or force of B, or it could have a name of some kind. 100 pounds. What's that? That's the magnitude, right? At an angle of 28 degrees. Notice the symbol. My little symbol. That's a vector pointing down. That would be this one. If this vector pointed up, that would be that one. But this one points down and it has the horizontal. That means this is the 28 degrees. That's this creature. At point A. That would be, go ahead.
After sense, what is the spelling?
Point,
No, sense.
arrow?
Okay, there.
Yeah, sorry. So this is this one. Good? Does that make sense? Yeah, no, yeah, okay. So then if I was gonna write this one, another way to write it, I'm gonna make this point C. I'm just gonna show you a couple of different ways to do it because there's even an easier way. So force at C. So that gives me the point of application right there. Right? And then I say 100 pounds. (28°). So that has it all. Force at C, 100 pounds, 28 degrees, census up and to the right. Questions? Pretty straightforward. We're not doing vectors yet. So this class does kind of flow that way. Sometimes I'll lecture on stuff that's not your homework, which can be confusing. I get that, but don't freak out when you get back and you're doing your homework. It's like, this is not vectors. That's okay. It's just the way it rolls sometimes because I got to push forward and you'll be working on material that's a little bit behind us sometimes. Okay.
Where I work with the vectors a lot, I work with the airports.
Oh, yeah.
So, but they have a distinct way how to study the vectors. They don't use what I learned in school. Completely different.
Types of forces. Last one, and then we'll be done. It's another guessing game.
How many are there?
Good question. There's really two that we're gonna, well, there's three that we will work with consistently. And then there's one extra one that I could probably figure out a problem that we could work with, but yeah, there's really just three. So don't think of like, oh, we have the force due to wind, or we have a force due to a heavy, you know, the building on the ground. Think of like types of forces. So pressure's a force for sure. So is pressure of a single point on an object, or is pressure over like an area? Oh, an area for sure, because what are the units of pressure? Pounds per inch square, and what would it be in the metric system? Guess. Pounds are the same kind of as what? Sir Isaac. Thank you. Newtons, and then inches and not feet, metric. Meters, okay. Meters squared. So a Newton meter squared, right, is like a PSI. We don't call it Newton meter square. We call it anyone know what that means? A Pascal. Google it. Super cool dude, man. He discovered pressure. So did Newton though, Sir Isaac Newton. So here's the deal. If you're using a scientist's name, the unit gets capitalized. So newtons are a capital N. Meters, that's no scientific dude or female, sorry. So it's lowercase, it's a meter, right? But a Pascal, that's a scientific dude, so it gets a P, capital PA. That's kind of fun. Anyway, yeah, so here's the unit this, which we will convert into this, and we will call them pascals for pressure. This is what we call a distributed load or force. Load and force, same thing. Distributed, meaning it's distributed over an area, right? So if we have distributed forces, what are the other kind of forces we have? Single point, which we call concentrated. On a beam, they look like this. Concentrated load. Distributed load. Those are the two primary ones we're going to work with. What would be the other load? Very common that we think about all the time. This beam is made of steel. I just made that up. And do you think it's heavy or light? Heavy. And how do we represent like the weight of something? What is the weight of something? It's gravity. And gravity is the other load that we work with all the time. It's really both a distributed load or a concentrated load, depending on how we're going to deal with it, right? If we use it as a concentrated load, it goes through the geometric center of the object. The geometric center of the object, right? Most beams are homogeneous, meaning their shape doesn't change. It's either a 4x6 and it's a 4x6 the whole way, right? Or it's a steel beam and it's the same cross section the whole way. So the geometric center of something like that is just halfway. It's pretty simple, right? If we end up with a beam that does this, some kind of fancy beam, then we have to figure out where that geometric center is. And we'll have methods of doing that. So gravity, distributed load, concentrated load. The other one that's fun to think about, but we don't have a lot of applications for, is magnetism. And that would be like an indirect load, right? That's where there's no contact, but you still get a load from something. There's not many of those. Wind would be what? What do you think wind is? Is it a concentrated load or is it distributed load? Definitely distributed load. Yeah. So a billboard, big sign, some big structure to hold it up. They had a real hard time with these in Troutdale, like 25 years ago. I don't know if anyone was around 25 years ago. I was driving to work and I used to take I-84 to come here because I lived down at Northeast. And man, it seemed like every winter the billboard is just taken out by the east winds. Just like, whoa, just really, guys, you can't figure out how to build a billboard and hold up to the wind. But they were just failing right and left. Yeah, so here's our billboard, and the wind load at the top of the billboard more substantial than the wind load at the bottom of the billboard, and usually that's a parabolic curve. So we'll do some parabolic load curves and figure this problem out, right? But it's definitely not a uniform distribution. It is a non-uniform distribution. So that's fun. All right. Good job. We're done. We'll see you Friday. We're going to have a quiz and it'll be on trigonometry.
What about me?
Boom.
Is,
I don't know. You're a problem. Been that way since the beginning, Jorge.
yeah, I know that.
All right. We'll do it online when you tell me when you want to do it.